Today we will discuss one of the most important concepts in calculus, the derivative of a function. In the last lesson we talked about a function like the amount of money earned by a student is a function of the number of hours. Alright, let's consider a similar function today. You earn $10 when you work for 1 hour. Now that means, again, when t represents the number of hours, y will represent the amount of money you earn, and you can write a function as y equal to 10t. Is that right? The time in hours is the input and y in dollars is the output. Now, how does the graph of y against time look like? It's a very common function, is that right? Y equal to mx. Now, if you draw the graph of y equal to 10t, it will look like this. When t equal to 1 hour, y equal to $10, t equal to 2 hours, y equal to $20, and so on. That's right. Now, when t equal to 1 hour, y equal to $10 is actually an ordered pair. So we would say t1 y1 equal to 110. Let's mark that ordered pair here. This is the ordered pair when t equal to 1 hour, y equal to $10. That's right. So this is our t1 and this is our y1. t1 equal to 1 hour, y1 equal to $10. When t equal to 4 hours, you work for 4 hours, you will be earning $40, and that is another ordered pair. And what is that ordered pair? t2 y2 equal to 440. I can mark that ordered pair here. This is t2 equal to 4, y2 equal to 40. That's right. This is t2 and this is your y2. Now tell me, what does this quantity t2 minus t1 represent? t2 minus t1, what does that represent? It actually represents the change in the number of hours you worked, or we can say it represents the change in the input. When there is a change in the input, there is a corresponding change in the output. So tell me, what does y2 minus y1 represent? This is y2, $40, y1 is $10, y2 minus y1 represents the corresponding change in the output when input changed by t2 minus t1. That's right. Now I have drawn a triangle here to represent these quantities. We will represent t2 minus t1 equal to delta t. This is t2, 4 hours. This is t1, that is 1 hour. So this length is t2 minus t1 and we will call it delta t. And in this case you know that t2 minus t1 is 4 minus 1, that is 3 hours. So delta t in this case is 3 hours. And we will also represent y2 minus y1 equal to delta y. So this is your y2, $40. This is your y1, $10. So this is the rise that is y2 minus y1. You see, when time changed t2 minus t1, y rises by y2 minus y1. So this is y2 minus y1 and we will represent that by delta y. Okay, tell me, what does delta y divided by delta t represent? The change in the output divided by the change in the input. What does it represent? So this is a ratio of the change in the output to the change in the input. And we call it the rate of change of the output with respect to the input. I can say, since the output is called y and the input is called t, I can say delta y by delta t is the rate of change of y with respect to t. The rate at which y changes with time. And you know how that rate of change is. You earn $10 an hour. So what is the rate of change of your earning? Every time you put in one more hour, your earning will go up by $10 more. So that $10 per hour is the rate of change. Let's have a look at it again. Now, in our example, delta t is 3 hours and delta y is $30. So delta y is $30 and delta t is 3 hours. Therefore, delta y by delta t is $30 divided by 3 hours. That is $10 per hour. That is the rate of pay you normally call. Is that right? In other words, this is the rate at which the output changes for each time the input changes by 1 unit. When you put in 1 more hour, you collect $10 more. That's right. Every time the input increases by 1 unit, the output increases by 10 units. That is the meaning of the rate of change. So, in the relation y equal to 10t, the rate of change of y with respect to t is 10. So when you look at the equation, you can actually figure out the rate of change. And you also know that this quantity delta y by delta t is the slope of this graph, isn't it? So what is the physical meaning of the slope of a graph? Slope of a graph is a measure of the rate of change. Now, generally you call it the rise over run, is that right? Rise is the change in the output. Run is the change in the input. So, when input changes by 1 unit, how much does the output rise? For a graph like this, which is a straight line, every time the input changes by 1 unit, the output changes by the same quantity. Look at that. When the input changes by 1 unit, the output changes by 10 units. It doesn't matter where you do it. The input changes by 1 unit, the output changes by 10 units. And this is true for all linear functions. You can see this is a linear function where the graph is a straight line. For a linear function, the rate of change is a constant. The rate of change remains a constant. All right, now tell me, what is the rate of change of the function f of x equal to 20x? Well, if you have the graph of this, it will go like this. Every time x changes by 1 unit, the output will change by 20 units. Is that right? Now, when x changes by 1 unit, f of x changes by 20 units. I want you to watch. Here I use f of x for the output, which is the same as y. Very often we use the y as the output, but f of x or f of t in this case, y can also be called f of t or f of x, g of x, h of x. They are all representations for the output of a function. All right, now tell me, what does it mean when you say the rate of change is $10 per hour? What do you really understand? We actually talked about it. It actually means that you work 1 more hour, you earn $10 more. Now, when the input changes by 1 unit, the output changes by 10 units. That is the meaning of that. Now, this rate of change of a function the rate of change of a function with respect to the input is called the derivative of the output. Now the output is also called the dependent variable, isn't it? A function has an independent variable and the dependent variable. Dependent variable is the output. The independent variable is the input. So derivative of the function is the rate of change of the output, which is the dependent variable, with respect to the input. That is the definition of the derivative. Now, in the case that we discussed, it's a very simple case. The function is a linear function. The derivative or the rate of change remains a constant. So this is the simplest case of defining a derivative. Now, how do we represent or write the derivative of y with respect to t? Now, earlier we said it's a measure of the change in the output divided by the change in the input. In other words, it's delta y divided by delta t. And how do you write the notation for a derivative? Now, instead of writing delta y by delta t, we write it as dy by dt. Now, dy by dt is the symbol or the notation for, look at the way I'm going to read it. We're going to read d by dt of y, the rate of change of y with respect to t. That is called d by dt of y. The rate of change of y with respect to t is called the derivative of y with respect to t. Now here, t is the independent variable and y is the dependent variable. So, on the other hand, if you have y as the dependent variable and x as the independent variable, how will you write the derivative? When t is the independent variable and y is the dependent variable, derivative is written as dy by dt. If x is the independent variable and y is the dependent variable, the derivative will be written as dy by dx, the derivative of y with respect to x, d by dx of y, the rate of change of y with respect to x. So x is here the independent variable and y is the dependent variable. Alright, if y equal to 10t, then what is dy by dt? What is the rate of change of y with respect to t? It is 10. That's right. If y equal to 25x, then what is dy by dx equal to? It will be 25. The rate of change of y with respect to x is 25. What does that mean again? When x changes by 1 unit, y will change by 25 units. That's the meaning in there. Okay. Now, the example we saw so far is the case of a linear function. That is, the rate of change is a constant. The graph of the function is a straight line. Its derivative will be a constant. Is that right? Because the slope of a straight line does not change. The linear function, the slope does not change. Now, on the other hand, think of a car that starts from rest, then increases its speed for a while, and then applies brakes and slows down and comes to a stop. Now, how does the position x of the car change with time? Now, have you understood the scenario I described for you? A car increases its speed. That is, actually, you are starting from the light changed to green. You put your foot down, the speed increases, then ahead you see a red light. So as the speed increases, You apply brakes, you reduce the speed, and then come to a stop. Now it will look like this. When t equal to 0, you are just starting. Now you cover this much distance in the first second, this much distance in the second second, this much in the third second. You can see your speed is increasing, and this much distance in the fourth second, and at the end of the fourth second you see the red light ahead of you. You put your foot on the brake. The distance now, the fifth second, the distance is less, the sixth second even less, and so on. Now how does the graph of x against time look like? You can see as the time interval t equal to 1, this is your x value. T equal to 2, x value is greater. At the end of t equal to 3 seconds, you can see from t equal to 2 to t equal to 3, the distance covered is even greater. So, remember, if the distance covered is the same every time interval, then you get a straight line graph. Is that right? Now, in this case, the graph is going to be curving up, because each time the time increases by 1 unit, the distance is going to increase greater each time. So you can see the graph will curve up. Now how about here? Each time the time changes by 1 unit, the distance decreases. In other words, the graph will curve down. So if you look at the graph I have drawn, for the first 4 seconds, the graph will curve up, and the next 2 or 3 seconds, the graph will curve down. That means, for the first 4 seconds, each second, the car covers more distance than the previous second. That's the curving up. For the next few seconds, each second, the car covers less distance than the previous one. You can see the curve, it's curving down. Alright, now since this is not a straight line, you can see curves up and then curves down. Now how do we find the rate of change in such a case? You see, the rate of change does not remain a constant. The rate of change keeps changing, because when t changes by 1 unit, the change in the output is not the same in the first second, in the second second, the third second, and so on. The rate of change is no longer a constant. So let's take 2 points, 2 positions of the car. So points A and B represents 2 positions of the car at times t1 and t2. This is position A and this is position B. And position A correspond to time t1. Position B correspond to, alright, we would say that position is y1. When the car is at point A, the position we call y1. That means at time t1, the car is at position y1. And the car is at B at time t2, and the position we will say is y2. Alright, so what is t2 minus t1? t2 minus t1 is this quantity, and we represent it by that length, and that is our delta t. This is the change in the time. Now, during this change in time, how much did the position change? Well, the change in position of the car during this time interval is y2 minus y1. That is this distance, and we call that delta y. Now tell me, in the case of the straight line graph, we said delta y by delta t is a measure of the rate of change. Now, if you take delta y by delta t here, does it give you a measure of the rate of change in that interval? No, it will not, because the change in position is not along a straight line. If it is along a straight line, then the rate of change will be delta y by delta t. Now, but we can do one thing. We can measure the slope of the straight line AB. If you join the line AB, we can measure the slope of that line. The slope of this line will be delta y by delta t. That's right. Now, we can say slope equal to delta y by delta t. Now, what is the physical significance of that? What does it actually mean? Now, this line AB is very often called the secant line of this curve. So, if this is the curve AB, then the line AB is called its secant line. So, delta y by delta t is the slope of the secant line joining points A and B. Now, what does slope of the secant line actually represent? If you now take the change in position of the car during a time interval delta t, this delta y by delta t actually represents an average change in position of the car. You see, the change in position doesn't remain a constant, but you can find an average change in position. So what does the slope of the secant line AB represent? It represents an average change of the position y with respect to t in that time interval delta t. That means in a situation like this where the change is not a constant, delta y by delta t does not give you the rate of change, but we can say it represents an average rate of change during this time interval, the average during that time interval. Now, the actual rate of change in such a case, the actual rate of change in a case like this has meaning only at one point, because as you put your foot down, at each point along the path of the car, the rate of change is different. So the rate of change has a meaning only at one point. What is the rate of change at A? The moment you move to B, the rate of change is different. You move to C, the rate of change is different. You move to another point, the rate of change is different. So the rate of change has meaning only at a given point in such a case. Now the rate of change at the point A, we can find the rate of change at the point A if we make this time interval very small and let the time interval come so close to zero that we can say for all practical purposes that time interval is zero. That means as the time interval becomes smaller and smaller, this point B will come closer and closer to A. Is that right? That means this secant line will almost become the line representing the curve itself at that time. So what we will do is, let's take point B over here. What we are doing is, we have now reduced the time interval. The delta t, previously the delta t was this. And now we take delta t much smaller. That means if this is position A, this is position B. And you can see the secant line and the curve itself, there isn't a lot of difference in there. They are almost the same there. Now, at the instant when delta t is very close to zero, we say the point B is almost at the point A. If you now bring B again closer and closer so that B is here, there will be no distinction between the secant line and the curve itself. And the line then becomes a tangent line at the point A. Is that right? Now, that is very important to know. That is, if I bring the point B, say here, then AB, the line AB and the curve AB will not be distinguishable, and the line then becomes almost a tangent drawn at A. Now, like this. That's right. So, delta y by delta t now is the slope of the tangent line. Now, when you say now, what does that now means? Now means when B is very close to A, so that the time delta t is very small, very close to 0. When that delta t is very close to 0, or we talked about limiting value, didn't we? So the limiting value of delta y by delta t, when this delta t is very close to 0, the line AB actually becomes the tangent at the point A. Then the rate of change at A will be the slope of that tangent line. You see how the secant line becomes the tangent line? How does the secant line becomes the tangent line? By bringing this point B closer and closer, such that the time interval delta t becomes very small. So the slope of the tangent line at A represents the rate of change at A. That means the rate of change at A is the rate of change at the instant when the object is at A, or at the instant t1. So the slope of the tangent line is called the instantaneous rate of change. And this is a measure of the derivative of the position function. You see, the derivative of the position function, like this, has a meaning only at one point, and it is called the instantaneous. At that particular instant, what is the rate of change at t equal to t1? It is the slope of the tangent line drawn at A. What is the rate of change at the instant t equal to t2? It is the slope of the tangent line at the point B. Now, if you are watching my pointer here, you can see the slope of the tangent line at A is positive. The slope of the tangent line at B is negative. What does that mean in the case of the motion of the car? At A, each time the time increases by 1 unit, the position is increasing. And that's the meaning of a positive slope. At B, with time, the position is decreasing, and you've got a negative slope there. So, again, what is the definition of derivative for a function like this? The slope of the tangent line at the point A is called the instantaneous rate of change, and that is a measure of the derivative of the position at t equal to t1. Now remember, the derivative will be different at different positions. The derivative is defined only at one position. So the derivative dy by dt is therefore the limiting value of delta y by delta t. What's the meaning of this again? The delta y by delta t in a big interval, we call this is the average rate of change in that interval. And when you make the interval shorter and shorter and shorter and shorter, when the delta t is so small that it's very close to 0, the value of delta y by delta t at that time is called dy by dt. The instantaneous rate of change of y with respect to t. And look at the way we write that in calculus. dy by dt is the limiting value of delta y by delta t when delta t approaches 0. In the limiting case, when delta t approaches 0, delta y by delta t is called dy by dt, which is the derivative of y with respect to t, and it is a measure of the slope of the tangent line drawn at the point A. That's right. This animation is from the University of Minnesota Math Department, and it shows how when the interval is made smaller, how the secant line eventually becomes the tangent line at this point. You can see the secant line, this is the average rate of change. The average rate of change becomes the instantaneous rate of change. Is that right? The secant line becomes the tangent line when delta t approaches 0. There you are. And that is an important concept in calculus. Now, here is another animation. I'm going to drag this red point and change this interval. Now, when this interval is made smaller and smaller so that delta x become equal to very close to 0, see what happens. This is the secant line now, and see how when the interval becomes smaller and smaller, how the secant line becomes almost the tangent line. You notice now the interval is so small that this line is now almost a tangent line at this point, and the slope of that line gives you the instantaneous rate of change at that instant, at that position, at that. All right, let's now look at the symbols that we use one more time. The derivative of x with respect to t, what is the definition of that? It's the limiting value of delta x over delta t. Delta x over delta t is the average rate of change in an interval delta t. The limiting value of that when delta t approaches 0 is called dx by dt, the derivative of x with respect to t, and we represent that by x prime. In other words, dx by dt is the same as x prime. Similarly, limit delta t approaches 0, delta y by delta t is dy by dt, and we also write it as y prime. The average rate of change of y with respect to t, the limiting value of that when delta t approaches 0 becomes the instantaneous rate of change. The slope of the secant line at that instant is called the derivative of y with respect to t, or y prime. Similarly, limit delta x approaches 0, delta y by delta x, this time the independent variable is x, is dy by dx, is also called y prime. Now, very often we use the symbol, whether it is with respect to t or with respect to x. So we need to specify the independent variable. The derivative of a function f of x with respect to x, we represent it as f prime of x. So f of x is the function, f prime of x is its derivative. All right. Now, how do we find the derivative of a function? We just talked about it. If y equal to 10x, what is the rate of change of y with respect to x? We found it is 10. If y equal to 20t, then delta y by delta t, or dy by dt, in that case will be 20, because the function is a linear function. Now, if f of x represents the function of x, then when x changes to x plus delta x, now look at this. When x equal to x, the function is f of x. Is that right? Just like when you work for 2 hours, the output is f of 2 equal to $20. So when the input is x, the output is f of x. Now the input is going to increase by a quantity called delta x. So this interval is delta x, so that this input value is x plus delta x. Now when the input is x plus delta x, the output is f of x plus delta x. Have you understood that? When the input is x, the output is f of x. When the input is x plus delta x, that means the input is now greater. The output becomes f of x plus delta x. In other words, when you say f of 2 equal to 20, f of 4 equal to 40. Is that right? So here, the input is x plus delta x. The output is f of x plus delta x. Now tell me, what does this quantity represent? F of x plus delta x minus f of x. That represents the change in the function value, the change in the output, or we can say the increase in the output in this case. A change is a better word. So f of x plus delta x minus f of x is a measure of the change in the function value or a change in the output, and we represent that by delta y, the change in the output. And this change in the output occurs when the input changed by delta x. So this is the change in the input, this is the change in the output. Delta y by delta x is the change in the output divided by the change in the input. The output when the input is x plus delta x is f of x plus delta x. The output when the input is x is f of x. So this output minus this output is your delta y. And that is a measure of the slope of the secant line, and we generally call it the average rate of change. And so the average rate of change is f of x plus delta x minus f of x all over delta x. So this is the average rate of change of this function from x equal to x to x equal to x plus delta x in that interval delta x. Alright, now this is a measure of the average rate of change in the interval delta x and is equal to the slope of the secant line. We talked about it. And this average rate of change becomes instantaneous rate of change when? When does this average rate of change becomes the instantaneous rate of change? When we make that interval very small, close to zero, when delta x becomes very, very close to zero. In other words, the limiting value of this ratio. And therefore, we say instantaneous rate of change is the limiting value when delta x approaches zero, the change in the function value divided by the change in the input. The change in the output divided by the change in the input. The limiting value of this when delta x approaches zero is what we call the instantaneous rate of change. That is, the instantaneous rate of change is the derivative of the function. If the function is f of x, its derivative is f prime x. And f prime x is a measure of the instantaneous rate of change. And it is obtained by the change in the function value divided by the change in the input. And we take the limiting value of it when delta x approaches zero. So look at the definition again. F prime of x, the derivative of f of x, is limit delta x approaches zero, f of x plus delta x minus f of x, that's a change in the function value, divided by the change in the input value. The change in the output divided by the change in the input, and we find the limiting value of that when delta x approaches zero. Let's practice this using a function like this. F of x equal to 2x plus 5. Now tell me, if I have a function like f of x equal to 2x, what is the rate of change? Well, we know that, we talked about it. It is 2. When x changes by 1 unit, y will change by 2 units. How about f of x equal to 2x plus 5? Let's use the definition of derivative. So our function f of x is 2x plus 5. How about f of x plus delta x? The input is now x plus delta x. Means replace your x by x plus delta x there. So if f of x equal to 2x plus 5, f of x plus delta x is 2 times x plus delta x plus 5. Now distribute there, it will be 2x plus 2 delta x plus 5. Now what is the change in the function value? That is f of x plus delta x, which is this quantity, minus f of x, which is this quantity. So that will be f of x plus delta x is this, minus, that's right, this is your f of x plus delta x, and minus your f of x is 2x plus 5. Now simplify this, distribute that negative sign, you get this. And you notice 2x minus 2x plus 5 minus 5 will go. What is left? That's equal to 2 delta x. So the change in the function value is 2 delta x. Alright, let's divide this change in the function value by delta x. What do you get if you divide 2 delta x by delta x? Delta x will cancel. That will give you 2. And you can see the average rate of change is 2. What is the instantaneous rate of change? Because 2 is a constant, the average rate of change and the instantaneous rate of change are the same. Why? Because the graph of this function is a straight line. There is no difference between average rate of change and the instantaneous rate of change. A difference occurs only when you have a graph that curves up or curves down. Then the average rate of change and the instantaneous rate of change are different. And one more thing I want you to notice. The derivative of f of x equal to 2x plus 5 is 2. And the derivative of f of x equal to 2x also is 2. That means this constant number really does not play a role in the derivative of a function because a constant does not change. Is that right? Alright. Therefore, we say limit delta x approaches 0, delta y by delta x equal to 2, or f prime of x equal to 2. The derivative of this function equal to 2. Let's practice the same with another function. Look at this. F of x equal to 2x squared plus 5x minus 3. If you know how the graph of this quadratic function looks, it will be a curve, curving up. Is that right? Okay, so this is your f of x. We start with the f of x. What is the next step? Find f of x plus delta x. Replace your x by x plus delta x. That means the input is now greater. So replace your x by x plus delta x. That will be 2 times x plus delta x all squared plus 5 times x plus delta x minus 3. Can you simplify this? How do you simplify this? X plus delta x all squared. That will be x squared plus 2x delta x plus delta x squared. That's how you expand. A plus b all squared is a squared plus 2ab plus b squared. So x plus delta x all squared is x squared plus 2x delta x plus delta x squared, and multiply that by 2, you get these 3 terms. So that will be 2x squared plus 4x delta x plus 2 delta x squared. These 3 terms come by expanding this and multiplying by 2. And distribute this plus 5x plus 5 delta x minus 3. This is f of x plus delta x. We now need to find f of x plus delta x minus f of x. Find the change in the function value. So what is f of x plus delta x minus f of x? F of x plus delta x is this whole quantity. Minus f of x is this quantity. Let's write that. So that will be, this is f of x plus delta x. Then subtract f of x. That's your f of x. And what will happen now? Well, distribute this negative sign. I have distributed that. Minus 2x squared minus 5x plus 3. And now simplify. If you notice, 2x squared minus 2x squared will go. Plus 5x minus 5x will go. Minus 3 plus 3 will go. You are left with 4x delta x plus 2 delta x all squared plus 5 delta x, and this is the change in the function value. Now here, if you notice, delta x is common, we can factor that out. So that will be delta x times 4x plus 2 delta x plus 5. This is the change in the function value. Now what's the next step? We find the average rate of change. Divide the change in the function value by the change in the input. So here, f of x plus delta x minus f of x over delta x is this quantity divided by delta x. And the delta x and the delta x will cancel. That will give you 4x plus 2 delta x plus 5. Now, what is this quantity? What do you call this? It is a change in the function value divided by the change in the input is the average rate of change. Now, when does the average rate of change becomes the instantaneous rate of change? When does delta x become very close to 0? In other words, we take the limiting value of this quantity when delta x approaches 0. So limit delta x approaches 0, the delta y by delta x. You can see the limiting value of this when delta x approaches 0 is obtained by replacing delta x by 0. So this term goes. So the limiting value of this is 4x plus 5. And what do you call this quantity? The limiting value of delta y by delta x when delta x approaches 0 is called dy by dx, or the derivative of the function, which we call f prime x. So f prime x is 4x plus 5. If f of x is 2x squared plus 5x minus 3, f prime of x is 4x plus 5. If you can remember this, I will ask you this in the next class. Alright. We talked about this as the derivative is the slope of the tangent line, didn't we? So derivative of a function is the instantaneous rate of change, which is the slope of the tangent line at a given instant. And this is the function we have been finding the derivative of. If f of x equal to 2x squared plus 5x minus 3, what is the derivative we just found? What is f prime x? F prime x is 4x plus 5. That's right. Now what is the meaning of f prime of negative 1? What is the instantaneous rate of change when x equal to negative 1? Now remember, the rate of change will be different at different points. As you move from point to point, the rate of change will be different. So what is the rate of change? What is the instantaneous rate of change at the instant when x equal to negative 1? Replace your x by negative 1, and that will give you 1. So at the instant when x equal to negative 1, the derivative is 4 times negative 1 plus 5. And look at this. This is the graph of 2x squared plus 5x minus 3. And here, this is x equal to -1. And f prime of -1 equal to 1 means the slope of the tangent line at that instant. Look at that slope. The slope of this tangent line is 1. So the slope of the tangent line at x equal to -1 is 1, means the instantaneous rate of change at this point is 1. It means at that instant, when x changes by 1 unit, y will also change by 1 unit. When the input changes by 1 unit, the output will change by 1 unit as well. At that instant. But if you move to another instant, the rate of change will be different. Alright, how about this? F prime of 0.5. What is f prime of 0.5? In f prime x, replace x by 0.5. That will give me 4 times 0.5 plus 5 equal to 7. So if you come to x equal to 0.5 will be, this is x equal to 1. So x equal to 0.5 is this. There you are. This is x equal to 0.5, and I have drawn the tangent line there, and the slope of that tangent line is 7. Now look at that. The calculator gave you the equation of the line, y equal to 7x minus 3.5. What does that 7 represent? It is the slope of that tangent line. So the derivative of this function at x equal to -1 is 1, means the slope of the tangent line drawn at that point at x equal to -1 is 1. The derivative of the function at x equal to 0.5 is 7, means the slope of the tangent line drawn at x equal to 0.5 is 7. Now that means when x changes by 1 unit here, y will change by 7 units. You can see the rate of change has dramatically changed when you move from point to point. Alright. Let's now find the derivative of square root of x using the same principle we used in the previous one. Alright, so f of x equal to square root of x. Next we find f of x plus delta x. F of x plus delta x is square root of x plus delta x. What is f of x plus delta x minus f of x? Well, this is f of x plus delta x minus this is your f of x. And now the change in the function divided by change in the input. This is the average rate of change. Average rate of change is, this is the change in the function, and the change in the input will be delta x. Alright, so delta y by delta x. This is the change in the y value, or the change in the output value, or change in the function value, anything that you want to use there. So delta y by delta x is the average rate of change. Now can you simplify this? In order to simplify, see what I have done, just like what we did in the previous class. I multiply the numerator and denominator by the quantity square root x plus delta x plus square root of x. Both numerator and denominator. Why did we do that? Again, this is of the form a minus b times a plus b. What is a minus b times a plus b? It is a squared minus b squared. So what does this become the numerator? It will be a squared, the square of this will be x plus delta x, minus b squared is square of this quantity minus x. Now look at the way the numerator simplified dramatically there. The denominator remained the same. And on the numerator, x and negative x cancels, and delta x will cancel, and the result is 1 over square root x plus delta x plus square root of x. And what is this quantity again? It is f of x plus delta x minus f of x over delta x. the delta y divided by delta x. Change in the function value divided by the change in the input. This is the average rate of change in this interval here. When does the average rate of change become the instantaneous rate of change? When the delta x approaches 0. So f prime of x is the limiting value when delta x approaches 0 of this quantity. And how do you get that? To find the limiting value when delta x approaches 0, set that delta x equal to 0. So that one will go. The denominator will then become square root x plus square root x. That is 1 over 2 square root of x. That means the derivative of square root of x with respect to x is 1 over 2 square root of x. I want you to remember that also. In fact, we found the derivative of two functions, well, three actually, but I want you to remember the derivative expressions of this. The derivative of f of x equal to square root of x is f prime of x is 1 over 2 square root of x. Let's do a problem that needs the application of the derivative. Find the equation of the tangent of f of x equal to square root of x at x equal to 1. Find the equation of the tangent line at x equal to 1 of the graph of f of x equal to square root of x. Now, in order to find the equation of a line, what are the information that you need? You need the slope of the line and a point through which the line passes. Now, can you obtain the slope of a tangent line? What is the slope of a tangent line at x equal to 1? The slope of a tangent line at a particular point is called the derivative of the function at that point. So what we need to do is find the derivative of this at x equal to 1. There I have the graph of square root of x. And at x equal to 1, I have drawn a tangent line, and that gives me the slope of the tangent line is 0.5. Let's see if that is correct. You know that the derivative of f of x equal to square root of x is f prime of x is 1 over 2 square root of x. We want to find the derivative at x equal to 1. So what is f prime of 1? Is 1 over 2 square root 1 equal to 1/2. The derivative of this function at x equal to 1 is 0.5. Now look at this. The graph of square root of x. The tangent line drawn at x equal to 0.5 has a slope of 0.5. The slope of the tangent line drawn at that point is a measure of the derivative of the function at that point. Is that right? So the slope of the tangent line is 1/2, and the point is x equal to 1. When x equal to 1, what is the value of the output y? F of 1 equal to 1. That means this point is x equal to 1, y equal to 1. That's right. So the point of tangency is 1, 1. Did you understand the meaning of that? The point of tangency is 1, 1. This point corresponds to x equal to 1, y equal to 1, and that is where we have drawn the tangent line. And the slope of that tangent line is 1/2. Can you now write the equation of the line? The equation of the line passing through the point x1, y1 and having a slope m is, how many of you can tell me the equation of a line that has a slope m and passing through the point x1, y1? Is y minus y1 equal to m times x minus x1. We know x1 is 1, y1 is 1, and m is 1/2. There you go. So y minus 1, that's your x1, y1, and that's your m value. y minus 1 equal to 1/2 times x minus 1, and take the 1 to the right hand side, we get y equal to 1/2 of x minus 1 plus 1. Distribute that 1/2, that will be 1/2 x minus 1/2, or that will simplify to y equal to 1/2 x plus 1/2, and this is the equation of the line. And this is the equation that we saw in the graph that I produced in the previous slide. Okay. A question for you. Is there a point in the domain of the function where the derivative is undefined? If you take a function like f of x equal to square root of x, is the derivative of that function defined in its entire domain? Now, what does that mean? Let me see if I can illustrate that for you. Now, if you recognize, this is the graph of y equal to square root of x. Now, remember, derivative is the slope of the tangent line drawn at a point. The derivative at this point, at this x value, is the slope of the tangent line at this point. Let me draw some tangent line for you. Now, if I take, say, x1 here, the derivative at x1 will be the slope of that tangent line. Is that right? The derivative at x2 will be the slope of this tangent line. Now tell me, what is the derivative at x equal to 0? What is the derivative of this function at x equal to 0? What will be the tangent line here? You can see the tangent line is actually the y-axis. It is a vertical line. What is the slope of a vertical line? The slope of a vertical line is undefined. Is that right? Therefore, the slope of the graph of y equal to square root of x at x equal to 0 is a vertical line. That means the derivative of this function is not defined at x equal to 0. Well, you can also say that the derivative f prime of x equal to 1 over 2 square root of x. And because that x is the denominator, at x equal to 0, the derivative is undefined. So, in the case of f of x equal to square root of x, when x equal to 0, the derivative is undefined. Now, there are similar cases. Let's also look at a couple of other cases where the derivative is undefined at certain points. All right? All right. Now, I want you to look at this diagram. Now, what is the derivative? If you can see my pointer, when it goes into the dark area, you will not be able to see it. But you see the point here? At that point, there is the graph of the function has a, we say, it is not smooth. Is that right? The curve is not smooth. That means at this point you can have two distinct tangent lines. Now, let me see if I can actually illustrate that by drawing another diagram. Now, this is how this point looked like. If you have in the graph of a function a sharp turn like this, now a tangent line at this point can be like this or like this. That means there can be more than one tangent line at one point. Now, if you have more than one tangent line at a point, can you talk about the rate of change at that point? Does the rate of change has a fixed value there? No. Therefore, we say if the graph of a function has such a sharp turn, then the derivative at that point is undefined. Why it is undefined? Because it can have a tangent line like this and also a tangent line like that. And the slope of those two tangent lines are different, isn't it? Yes. Now, the slope of the tangent line here will be different from the slope over there. So you've got two tangent lines at the same point and they have different slopes. Therefore, we say the slope of the tangent line at this point is undefined. That's right. Okay. So for the graph shown on the right, two tangent lines are possible at x equal to 0.6. That means the derivative at that point is undefined. The derivative of a function is undefined at points where the graph of the function is not smooth. Okay, how about here? You got a similar situation I just illustrated earlier. You can see the tangent line corresponding to x equal to, what is this? What x value is this? 0.5? Now, the tangent line is vertical. What is the slope of a vertical tangent line? So at x equal to 0, the tangent line is vertical and the slope of a vertical line is undefined. So at points where the graph of a function has a sharp turn or the graph of a function has a vertical tangent line, the derivative is undefined. Alright, now I have drawn some cases where the derivative is undefined. How about this function? You notice here there is a break in the function graph. So the derivative is undefined at x equal to 2. This is x equal to 0, 1, 2. Because the function is not continuous there. There's a break in the function graph there. So where the function has a break, the derivative is undefined. The second case, the function is undefined, is here. We just talked about it, where the function curve is not smooth. You have a sharp turn there. The derivative is undefined at x equal to 3 and x equal to -3 because two tangent lines are possible at these 2 points. That means there is no definite value of the derivative at these 2 points. Another instant where the derivative is undefined is if you take a point on the graph here, the tangent line is vertical and that means the derivative is undefined. So the derivative is undefined at x equal to 0 because the tangent line is vertical at that point. Now we have just laid the foundation for finding the derivative of a function. I want you to understand the meaning of derivative and the fundamental idea of the limiting value of delta y by delta x as the basic definition of the derivative of a function. Now in the next lesson we will develop better methods of using mathematical formulae to find the derivative of functions. In the meantime, I will ask you the derivative of at least the two functions we talked about in this lesson. All right?